Hello and welcome to another episode about the minirack. In the previous episode, we did the physical build, and I said for the second video I would go through the software configuration. But before we do that software configuration, I thought we'd first take a look at a few hardware enhancements and a little bit about the networking, which has a few complications that are interesting. So we'll start with the hardware, and let's take a look at what changes we've made over the last couple days. And so here we are, we have the chassis set up here, and I added a little screen to the front that's plugged into one of the Raspberry Pis. And that screen will eventually be used to display some data from Grafana once we get that configured. And you'll be able to see things like temperature and CPU usage. A second thing I worked on was a little bit about thermal management. So these MSO1s produce quite a bit of heat, and they generally produce the heat out of the back of the unit. And if you run them at pretty full load, that's quite a bit of CPU power plus memory plus the 10 gig networking. And so I did a little bit of work on heat management. The first thing I did was I made a little fan module here. This front cover came with the from DeskPi with the T11. And so I just bolted some fans that actually fit quite well there. And I think there probably is a market to make a fan module for this that can blow air. And that blows air out the back across the two 10 gig switches, which tend to get pretty warm. And then I also added here to the top two fans that pull air from the bottom up to the top of the case. And that probably made the biggest difference in overall heat because the heat rises, of course, and it's being produced by the units back here. And then I temporarily added another fan here on the rear. And this fan pulls air back out of the MSO1s. And this is just a temporary thing. I just have it attached to the rack there. I think the right thing to do would be to make a 3D printed little bracket that goes on here that has a couple of fans in it that pulls air out past the MSO1s. And so that's something I'm going to try to work on. There is a little fan controller here for the other two fans. And then for the top fan, there is a little controller right here. And so it's got quite a bit. If you turn it up, it's quite a bit louder. And it pulls quite a bit of air. And then I also added a little temperature probe there so we can see what the temperature of the air coming out of the unit is. And so all those things has made it improve the thermal overall. I think there's still a little more to do. It was recommended from a comment on my previous video that I should pull the MSO1s out and look at the thermal paste on the CPU. And so I haven't done that yet, but I will. And I'll do some measurements before and after to see what kind of difference it makes. But as with everything, I think there's always a little more we can do on the thermal management to improve this. But with that in mind, let's go take a look at what the networking stack is and how the network's configured, and a little bit about a few of the glitches that I'd sort of discovered along the way. So let's dig into the networking. And so I have a little diagram here showing the three Proxmox nodes and the NAS storage along with a little switch and then the firewall. And so there are three real networks portrayed on this page. The first is the red network, which is using the 2.5 gig ports on each of these devices. And that's the primary front end and management interface for those three boxes. That's attached to this little switch here and then attached to the firewall, which then gives you the outside world. If I could find a switch that fits in the 10-inch rack that has enough ports, you could do two 2.5 gig links and LACP them together. So that'd be a good thing to do because you have the ports on the boxes for that. It just requires a little more switch capacity than I have set up right now. So that provides sort of this primary internal network, which is 10.170. Now these boxes also have two SFP plus ports on them. And there are two SFP plus switches, each with 4 ports. Now, I wish the switches had 5 ports because 4 ports is just slightly not enough for some things. But we have 2 of those 4-port switches. And so I've decided to make it such that each of the set of 10 gigs for the Proxmox, one set, these blue ones here, are connected together into one of those switches. And so you see the blue line here for each of the 3 Proxmox nodes, plus the network attached storage. And so that blue network represents what I would call the storage network. It's the network used by the Proxmox servers to read and write from the storage being exported by the NAS. In this case, it's over NFS. And so that gives you a 10 gig network dedicated for just the storage read and write. This NAS, it has 3 NVMe SSDs in it. So internally, even though it's running RAID Z, it can read and write internally faster than the 1 GB per second you get over a 10 gig network. So the network's probably the limiting factor in most cases. But it does mean we can max out that 10 gig network and take as much advantage of it as possible. And so that is your primary storage network. The second network here, the green network, only goes to the 3 Proxmox nodes. And that's configured to be the Proxmox network for migration. So the node clustering is managed over that network. So when you migrate a VM from node A to node B, that is done over that dedicated 10 gig network. There's only 3 ports on that 4-port switch, so we have an extra port left. And I may eventually try to figure out a way to wire that in so we could get 10 gig traffic from outside. But for now, we have that network dedicated for the Proxmox migration, and then the 10 gig storage network to the NAS for the storage. Now, the last thing is this idea of this little Thunderbolt network. And each one of the machines has 2 Thunderbolt 4/USB 4 ports on them. And it is possible to run networking over those interfaces, and they're connected up such that each box has 1 wire going to each of the other 2 boxes. So it's a little bit like a ring where every box can touch every other box, and it gives you a direct connection from each machine to each other machine. But if you were to just run networking on there, just raw networking with IP addresses, it would be 2 different networks. And so a given machine would have to have a network address on each one of these ports. And then the other side would have to also be that other network. And it can be done, but it makes it difficult to do Ceph because you'd have to have a slightly different config on each of the 3 nodes because the way the other machines would appear will be different. You can fool up using name services and hard coding host files, but it makes for something that's not particularly resilient. So the solution for that is to run a routing protocol over those connections so that effectively there's 1 IP address that is virtually available on both of the connections to both of the other machines. And it's a really cool thing that someone else has already figured out, and we'll go through that configuration and take a look at their documentation of how to do that. So let's do a little bit about the networking. So we have these 10 gig networks. I'm going to go over here. So we have each of the machines. These are the 3 Proxmox nodes. And each one has, running screen here, each one has in a separate window, it has iPerf 3 running. So as an example, if we do IP address, we can see this ENP87 and the ENP89. Those are the 2 2.5 gig interfaces. Only one of them is turned on right now. You can see it says up here. There's no IP address here because it's actually down here on the VMBR, the virtual interface. And that's so that the VMs running on the box can also use it. You can see the address 10.170.1.100. This .100 is the sort of number for this box. This other box is 101, and the next one's 102. And so we can, for instance, we can ping 10.170.1.101, and that's pinging the second green box here. And the same with 102. Now, if we go back again here and look, we also can see this ENP2 P0 is one of the 2 10 gig interfaces, and here's the second one. And you can see that one of them has a 10.172 network, and one has a 10.171 network. So the 10.171 is the network for storage, the 172 is the network for the cluster communications. And so, as before, we can ping 10.171.1.101, which is pinging this green box over the storage network. And we can also go to 172 and ping it over the Proxmox network. So that works well. So let's talk about the performance of those. If I do iPerf 3-C and I use the 170.1.101, if I use the main 2.5 gig network, this is actually going into a 1 gig switch right now. And so sure enough, we'll do 2 threads. We get 1 gigabit connection. And so that's going from this green box or this purple box to this green box. So that works as expected. You can do the same thing to 102, which is to the red box, and you get 1 gig. So that works as you'd expect. Now we can also go back and let's go on the 171 network, which is the storage network. And of course we get right at 10 gigabits a second. That's what you'd expect to see on a 10 gig network. We can do the same thing to the other node. and we see we get 10 gig. We can even go to 103, which is the IP address of the NAS. And sure enough, we get 10 gig. So that 10 gig network for the NAS works as you'd expect. It's a 10 gig network with really nothing on it except for these 4 boxes. You can run it in reverse. So it does the other direction. Instead of sending, it's receiving, and you get 10 gig. And perhaps most importantly, if you do bi-directional, it'll run the tests in parallel, both a send and a receive in parallel. And we'll let this run here, and you will get basically right at 9.4, 9.5 gigabits per second in both directions in parallel. So we can see the sum RX received at 9.4 and the sum TX at 9.4. And so it is truly full duplex in that each box can fully receive and transmit at 10 gigabit at the same time. And that's an important aspect of a true full duplex network. So that all works as you would expect. So the 10 gig networks, both the first and the second one, work at 10 gig pretty easily. So let's switch gears and talk about the Thunderbolt stuff. And I have the web page pulled up here somewhere. Here it is. That is, let me go back to the top of this here. That is where a number of people have been working on how to get this Thunderbolt networking to work. And so this description here just tells you what you need to do. So the first one is prepare the Thunderbolt configuration. And so there are a couple simple things, and you do this on each of the nodes. And so there's a kernel module you have to load for Thunderbolt, Thunderbolt Net. There's a couple things you have to put in the interface file. It creates an interface called EN05 and EN06 to represent the 2 Thunderbolt interfaces. There's a little script you put on here so that when the Thunderbolt interfaces pop up, they get renamed to the same thing every time, this EN05. This text here mentions that this PCI path here is something you need to dynamically discover. It tells you how to do that. It's pretty easy. This is what those IDs are on the MSO1. If you use a different kind of box, the Thunderbolt PCI IDs will be different. So you'll need these for the 2 Thunderbolt interfaces. They add some scripts to make sure that if you unplug or replug in the interface or on a reboot, that the interface is brought back up again. Again, the instructions are relatively easy to follow. And then the next part is the enabling IP connectivity, which we're going to go through this here. And this has been sort of an evolving doc, but it has you create a couple files to enable the Thunderbolt interface itself. This particular one, the interfaces D Thunderbolt, you do it on all 3 machines. This right here is the IP address that you're going to use for each machine. Actually, there's 2 of them, an IPv4 and IPv6. Make sure you change this to, could be 81 for the first machine, 82 for the second machine. I use 100, 101, 102. So change these IP addresses for this script on each individual machine. It mentions that only in passing, and so you wouldn't want to just paste this script in directly because this is just one particular IP address. Then you enable IP forwarding, which is a few variables you commit or you uncomment. You would then install FRR, which is the software that runs the routing that talks from machine to machine to figure out how to make a connection between them. There's a couple of scripts you have to install on that. You then open the Open Fabric by running this little shell that allows you to configure the FRR, and you paste in this config here. And the one important thing I'll note here, and it mentions this here, but if it isn't clear, that at the very bottom here, this little X right here, that's the number that should be different for each node. So on node 1, you should make this 1. On node 2, make it 2. On 3, make it 3. If you mess it up, it won't work. But you paste this into the application here and then save it as a configuration. And once you do that, and the Thunderbolts are plugged in, then the FRR runs. It will discover the other 2 nodes and then build a little routing table. And it tells you if you run this command right here, and we will pop over to one of the boxes here, and we'll run that command. And sure enough, you can see that on this node, we're on 100, we can see 101 across the link and 102 across the link. And so this little dynamic table, and if you do that on each machine can see the other 2 machines and know how to get to them. And sure enough, over here we can ping 10.174, which is that network, 0.101. So that's pinging from this machine to the green machine over the network, and it works perfectly. And the same is true if we ping to 102. So that's the other node over here. It works perfectly. Now, one neat thing is if I go over there, and you can see the ping times are about 0.5 milliseconds, 0.4 milliseconds. If I unplug one of the Thunderbolt cables, particularly the one going from this machine to the red machine. If I unplug that one, you'll see that it will have one packet that's maybe a millisecond or 2 milliseconds, sometimes a little longer, and then it'll converge back to about 1 millisecond. And the reason is that the routing's detected that one of the links gone down, but it then routes you through MS01B, which is the second box. And so it's good in the sense that it's meant to be dynamic, and if you have one cable that fails, it will try to find the path through to the other box. Now, in reality, you'd want to know if one of the cables failed, because you wouldn't want Ceph to be routing all traffic through another node to get there, because in Ceph, with only 3 nodes, you're writing to all the boxes. So that would literally half the bandwidth you'd have, because you'd be fighting going through the second box to get to the third box. But in any case, so the IP connectivity works perfectly here. And if we do iperf3, and let's go 10.174.0.101. So we'll go to the we'll go to the C box, and we're going to do 4 threads. And what we'll see here is you get about 26 gigabit per second. And this is pretty reliable. You'll get around that 26, almost 27 gigabit per second in both directions to all the machines from all of the other machines. And again, if you go unplug one of the links so that's broken, the one that you have to hop twice, you do get about half the bandwidth. It does, in fact, make it quite a bit slower. But you're getting about 26, 27 gigabit per second. Now, a couple important things. One is mentioned on the first page of this GitHub about, sorry, not that one, this one, about configuring it. And they talk about slow Thunderbolt performance. And this is in fact true. With the MSO1s, you do want to make sure you turn on the IO MMU, which is a setting you put in the grub file. You definitely have to do that. And the second thing is you can pin the Thunderbolt driver to only run on P cores. And you can see a little command here to see what cores you have. And if we go to one of these boxes, you can see we have 12 P cores and the rest are E cores. And so this command will create a little script that runs that makes it when those interfaces come up, they always get bound to one of the CPUs that is a P core. Do both of these things if you're running an MSO1, and certainly on any platform, make sure you understand if you have P and E cores, you want to make sure that you do this change, and make sure you enable the IOMMU on, I think, probably any box that it's on. If you don't do that, then the numbers you see here will be either like 15 gigabit or 22 gigabit, and it appears to be a little variable. I think when it's running on the E cores, you only get 15. Occasionally it's a little bit weird though, so you'll notice it. It's not as fast, and it's not reliably fast if you don't make those changes. So make those changes so that you get the most performance. You then get a real 20, almost 27 gigabit per second connection between the machines. Now, a question you might be asking is, shouldn't that be 40? Because this is USB 4 / Thunderbolt 4, and the USB 4 data rate at the highest data rate, and of course this is a cable that's only 8 inches long, is 40 gigabit a second. Now there's a little bit of overhead in the encoding scheme, so it's really 39. With the USB framing overhead for the network, it's more like 36. But it's not 26. It should be more like 36 or 37. And I think the reason, I went and looked at the data sheet for the Intel 12 and 1300 CPUs along with the PCH. And together those two have everything about the implementation of USB 4. And from what I can tell on both the 12 and the 13s, the USB 4 interfaces, there are 2 of them, they support the 40 gigabit per second line rate, but internal to the mapping from there to the CPU, it lists it as being limited to about 3 gigabytes a second as a peak transfer rate from that interface into the CPU. And there are 2 lanes for that, and they're both limited at that speed. And sure enough, that number corresponds with very close to what that number would be. Likely there's some overhead. And so I think that's why you really don't get 40, you get more close to like 27 or so, because of a limitation in that implementation of USB 4. And it could have to do with the implementation of the networking layer as well, which I haven't really investigated much. But this appears to be what a lot of people see, at least on these particular machines. So it's possible if you had a dedicated PCIe 4x4 lane Thunderbolt card, maybe that one would get you the real 40 gigabit per second. Keep in mind, USB 4 also has an 80 gigabit standard as well, so you could potentially buy an interface that does that, and you might be able to get 80 gigabit. In any case, getting 26, 27 gigabit is fantastic, but there is one thing to note that's different than a normal interface. If I do, let's do 4 and do dash dash bidir. You'll remember before on the 10 gig, you really get 10 gig in both directions. However, if we run this, we get slightly less performance in both directions. And I'll show you here. You end up getting around 20, so we get 19.4 in the receive, and the transmit 19.8. So about 20 gigabit in each of the two directions. So it's slightly slower in full bidirectional than the peak in one direction. And that likely is related to something to do with that, the speed of that interconnection between the USB interface itself and the resulting bus that connects into the processor. At least that'd be my guess. And so realistically, you might describe this as a 20 gigabit network, not a 30 gigabit network or 27, but it does burst a little fast in one direction. Now with Ceph, that will be reasonably useful. In many cases, you're either going to be reading or writing for a given transaction. And so it's possible that peak speed of 27 is what you're going to experience. Even if it's not, having a reliable 20 gigabit between all of the nodes is really good and will help make Ceph more useful. So with that, we're going to take a quick look at a little bit of the software side of things. I mentioned in here that we have a little OPN Sense firewall, which I have configured here, and I have a bunch of port forwards configured so that I can talk to it because it's on its own little network. Here is the Proxmox cluster, and so there's 3 nodes in the cluster. They're added together, and if we go to cluster, you can see the cluster nodes are set to do the clustering over that 172 network. So they're over that dedicated 10 gig network for the clustering. If we go to storage, the VMs and ISOs are mounted over NFS, and you can see those are over the 171 network. So we have one network for storage, one network for the Proxmox migration. And so these 3 nodes are all up and running in a cluster. And I also then installed one VM here that I call the monitoring VM. And it's just an Ubuntu image. And on that machine, I installed 3 things. And let's pop over here. I have a login to that machine. The first is I installed Prometheus. And if we look at Prometheus's configuration, the default Prometheus installation, you can just install it. And this is what it comes with. It'll look at localhost for some alerts, and it will look at localhost for a thing called Prometheus Node Exporter. And it gets installed by default, and it runs. And the Node Exporter executes, and it generates a interface on port 9100, and it exposes a bunch of metrics from that machine. And so by default, the Prometheus install is set to at least look at itself, the machine that's running on, and get statistics. So I installed Prometheus. Very simple, it's like 4 lines to install it. The default config comes out of the box and works. And if you install it, you can even go to a web page that it exposes and see all the stuff that it's collected. So that's the first thing I did. The second thing is that I went and installed Prometheus Node Exporter on all 3 of the Proxmox nodes plus the file server. And that you can see here, it's in opt Node Exporter. It's just a single executable, and there's virtually no config. It runs, and if we do netstat, let's see, -ap and grep for 9100, we will see that Node Explorer is running, and it's outputting, making it available on port 9100. And so if you go to each of the 3 nodes plus the file server and install Node Exporter, all you have to do is get it running. It runs the service. You're good to go. If you then go into the config file on Prometheus, you just add in this line here, the targets. By default, it'll have just localhost. You just add in the 3, or in this case, the 4 other nodes that I want to go collect from. And the idea is that Prometheus will continually run every 15 seconds and go grab data from all 4 of these nodes, plus the internal one, and put it into its internal database. And that's all you have to do. Prometheus is now running and collecting data. And if you happen to go to the Prometheus interface, you can see what things it's heard from, what variables it's seen, and even get a graph of them. And then you can even see what particular machines are sending in data under this, this name. So this tells you that all of this data is being dropped into Prometheus and being collected. So now that it's there and you have some useful data from each of our nodes, what can you do with it? And the answer is you then install Grafana. And when you install Grafana, it installs easily, one command to do it. You log in as admin. You can create your own dashboards. There is a dashboard called Node Exporter Full that's on the Grafana website, and you can just import it by node ID. And it is one designed to use with Node Exporter if it's running into a Prometheus database. And so all you'll really do is install the dashboard, put the data source to your Prometheus, which will be the first config you put on there. And then you can see each of the different boxes that are monitoring, and then you can see a bunch of things that are being exported by that node exporter. Things like CPU and memory and disk, and even down here, let's see, there is some temperature stuff, and I actually added this one to be a little bigger. So this shows the CPU core temperatures for this particular node. And so all these data elements are being logged automatically by the node exporter, dumped into Prometheus, where they hang out, and then Grafana allows you to look into Prometheus and see that data and make graphs. And this is super easy to configure. It's really just out of the box configuring with no real tweaking. And then you have now the ability to then make some custom dashboards that can say, well, for each of the 3 nodes in Proxmox, here's their load. And so I will probably start working on a custom dashboard that I can display on the little display on my rack, as well as one that I can use to do all the monitoring. Now, one thing about thermals that's interesting is that if we go over here, so I think that I have, let's see. Yeah, so this is that file server, which is the 4th of the MSO1s. If I run stress ng, which is a task that will stress it, I'm going to run 1 core's worth of work, and we're going to put it on core number 7. So if I run that, and then I think I can go to here. I have btop running. And sure enough, you see that core 7 is now at 100%. So starting to heat up a little bit. If we go back to the graph, and this was me doing this earlier today, eventually I'll start showing in data here. You can see that the particular core we're running on and a couple of the cores nearby or temperatures nearby start to get pretty warm. So here we are at 85, 86, almost 90 degrees C. It doesn't hit the thermal limit of 100 C, but it does get pretty close though. And so I think that's part of it is maybe my needing to go in and put some better thermal paste. And the second one is that I do think that I'm going to work on a way to get a little more airflow coming in or out of those MSO1s, either with some small fan that goes in the front or a small fan that goes in the rear that can extract air a little faster. Here you can see it coming up as the cores warm up a little bit. And if you run it with something with all of the cores busy, the CPU does get to 85 degrees C, which is pretty warm. And at that point, it will certainly be throttling the clock rate a little bit. And so thermal considerations are something we have to kind of work on for sure. So that is a rough description of how I have it hooked up, how I did the Thunderbolt networking. I will put a link to this fantastic page in the description that talks about how to configure Thunderbolt networking. And this is being updated a lot, so keep an eye on this page. There are a lot of good comments in there about different ways to make it work. If you get it working properly, you should be getting, at least on the MSO1s, in that 26 gigabit per second connection between each of the machines. If you're not, then you might want to look into that a little bit and see what you can do. And so this is where we are with our little mini lab. So the next thing is I'm going to start installing some services and also work a little bit more on the thermal management, as well as install and configure Ceph. I have the networking configured to allow us to do Ceph, but I haven't turned Ceph on yet. So in one of the next videos, we will get that configured, and then we'll do a little bit of benchmarking between the Ceph over 25 gig versus the NAS storage over 10 gig. That's it for now. Thanks.